Hey there, folks. In this video, we're going to be talking about the week 5 Alex assignment, and this was the last unit we had left off on before the whole COVID situation had happened and we stopped seeing each other in person. So this one should actually be pretty fresh in our heads. And judging by your performance on quizzes and tests, I think most of you guys are going to breeze right through this. So that's definitely good to see. All right. The first few problems are going to be the exact same. So I'll explain number one kind of in depth, number two kind of quicker, and then I'm just going to show you the answers for three, four, and five just because they're so similar. So when we do these problems, when we're simplifying a radical, you are looking for pairs of factors. So we're going to make a little factor tree for the 18, and then we're going to break that down into its prime factors. Primes meaning they can't be divided by anything other than 1 and itself. And once we have our prime factorization, we're going to look for pairs. Pairs of numbers, so like right here, I've got a pair of 3s. Pairs of numbers can get pulled out of the radical. Numbers that got left all by themselves, they have to stay underneath. The same holds true for variables. Here I have t to the 12th. Well, that's the same thing as me just listing out 12 t's. So out of that, how many pairs of t's could I make? I could have 6. If I have 5 u's, how many pairs of u's could I make? Well, I could have 2 pairs with 1 left over. So when we go through and tackle all that, this is what our final answer will be. We have our pair of 3s on the outside. We have the 2 stuck inside here. From the t's, we had 12 t's, which means there's 6 pairs and nothing left over. We had 5 u's. Out of that, we can make 2 pairs with 1 left over. And that would be our final answer. All right, number 2, we're going to break down the 20. I chose to go 4 and 5. If you do 10 and 2, you'll get the exact same answer. It doesn't matter. Every single number has its own unique prime factorization. I got a pair of 2's and a single 5. So 2 on the outside, 5 on the inside. I've got 3 x's. So that's one pair. So 1 x on the outside, 1 on the inside. 12 w's. That would be 6 on the outside for 6 pairs. So that is what our answer will look like. All right. 5 is a little bit more challenging. Not much, but for 3 and 4, here you go. Here are the answers. If you need to pause the video to kind of reverse engineer anything, please feel free to do so. Number 5 is when we're going to start getting into higher degree radicals. So higher degree radicals means they have some sort of an index number. In this case, it's an index of 3. So I'm no longer taking the square root. I'm now taking the third root of this expression 54y12z13. Previously, we looked for pairs. That's no longer the case. Pairs are only good for square roots. We don't have a square root, we have a third root. So now I need to find groups of 3, or whatever that index number was. So if I'm taking a fourth root, I need groups of 4. So if I break down 54, I chose to do it with 9 and 6. You could do 2 and 27. Does not matter. I'm noticing I have 3 3s. So I have a triplet set of 3 that gets pulled out, and then a 2 is stuck all by itself, so that gets stuck inside. So the triplets get pulled out, whatever I'm able to group up, and the lonesome factor stays inside. With the exponents here, if I have 12 y's, that means I can make 4 groups of 3, and if I have 13 z's, I can make 4 groups of 3 with 1 left over. All right, let's see some other higher degrees. For number 6, we are no longer looking for pairs or groups of 3. For this one, we're actually looking for groups of 5. Little side note, anytime you see a group of 5 or a fifth root, I would bet money that it's going to be a group of 5 2's. Because if we had 3's or 4's or whatever, that number would be insanely huge. All right, so the process is still the same. You're going to factor this out however you choose to do it. I just chose to divide by 2 a whole bunch of times, so you can see mine kind of got messy. But you're going to look for a group of 5. I have 5 2's and then a lonesome 5 left over, so that stays underneath. And then for exponents, we're not looking for groups of 2 or 3 anymore. We're looking for groups of 5. So if I have 11 x's, that means I can make 2 groups of 5. That accounts for 10 of them with 1 left over. Holy smokes. And let me just take a sidestep here, people. It is April 14th, just shy of noon. And I'm looking outside and it is snowing right now. What the heck is happening? Anyways, I digress. All right, number 7. We're looking for groups of 4. So factor down 80 however you choose to do so. Look for groups of 4 numbers. Same thing goes for your exponents. 8, same thing. Look for groups of 3. Again, you guys have seen these problems before. I'm not too worried about it. All right, 9. 9 has a little bit more work. Very similar to 10 here. So when we're talking about adding or subtracting, right? So this one we're subtracting, this one we're adding. If you are adding or subtracting, you have to have the same radical. So rad 27 cannot add or subtract to other rad 27s. A rad 3 can add or subtract to other rad 3s, or maybe like a rad 7 to other rad 7s, but they have to have the same number inside the radical, or the same radicand, if you will. So what I'm going to do is I'm going to go through and break down, okay, maybe 27 breaks down into something smaller, and it's a square root, so I'm looking for groups of 2. So I got a pair of 3s with the 3 left over, and then this one's got a 3 left over. Okay, so now we're cooking. So here's what this turns into. Negative rad 27 is really just negative rad 3, and a rad 12 turns into a 2 rad 3. There's still that 5 hanging out up front. So if I did negative 3 minus 5 times 2, that's 10. Negative 3 minus 10 is negative 13, rad 3. It's basically like adding like terms with variables. If that was a negative 3x minus 5 times 2x, we would get negative 13x. Number 10 is going to be the exact same logic. Break down each radical and then combine them with matching radicals. All right, number 11. When we are multiplying, numbers on the outside, coefficients, can multiply to other coefficients. Here there is no coefficient, so I could pretend there's like a 1 hanging out front. So that's going to be 3 times 1, so just 3. Then the inside numbers, the radicands, can multiply to other radicands. So 20 times 48. That's going to be, let's see, 48 times 2 is 960. That's a huge number, and forgive me for sounding lazy, but I'm kind of lazy. I don't want to break down a huge number. So what I'm actually going to do is break down each one of these independently and just see what happens from there. So 20 breaks down into a 2 rad 5. Then a 48 breaks down into a 4 rad 3. Now I'll do the same thing I was talking about before, where I can take my outside numbers, the 6 and the 4, multiplying those together, and I can take my inside numbers, the 5 and the 3, multiply those together, and I'll get 24 rad 15. So for these, you can go through and multiply it right off the bat and then simplify later, or you can simplify right off the bat, then multiply. If you do that second route, you might have to multiply it at the very end. Fortunately for this one, 15 wouldn't really break down into any pairs. So not a whole lot that I can do there. All right, number 12. I could simplify each radical, but at the same time, I could just do 2 times 8. That's not too terrible, right? I know 2 times 8, that's just 16. Well, now this is just a straight up radical that I'm used to simplifying. So there we go. Number 13. We have some distribution that has to take place. So we are going to distribute, or FOIL, everyone's favorite 4-letter F word, one parenthesis chunk into the other. Now when we do this, we're going to have 4 separate terms. There we are, the 4 terms. And that comes from 2 times 2 rad 10, 4 rad 10, 2 times negative 4, negative 8, rad 6 times 2 rad 10, so on and so on. So we have 4 terms, and then we have to check maybe some of these break down. And you can kind of see off to the side I have it written. Rad 60 is actually the same as 2 rad 15. So 2 times rad 60 would be 4 rad 15. So that could actually simplify a little bit. 14 is going to be the exact same. We simplify, FOIL things out. This one is going to be kind of unique though, because I know that the square root of 36 is just 6. So that's really 9 times 6. And I know the square root of 49 is just 7. And then these two in the middle, these both have a rad 42. So I can go ahead and combine those. So this one's actually going to reduce to just 2 terms. Fun. 15 and 16 are the exact same. We have to rationalize the denominator. We do not like having radicals in the denominator of a fraction. So in order to accommodate that, just multiply top and bottom by the square root of 5, or whatever square root is in the denominator. What's going to happen when we do that is down below, square root of 5 times square root of 5 is the square root of 25, which is just 5. So that turns into a plain old number. And then up top, yeah, we'll have a radical still, but we don't really care about radicals in the numerator. So you'll see here, I've gotten rid of that square root sign in the denominator. 16 is going to behave the same. Instead of having it written as just one single radical, I find it beneficial to split it up. So I have a set numerator and denominator. From there, we would get rad 42 over 6. 17 is going to be slightly new. All right, and that's because we have not only an index of a radical, but we also have an exponent, and we want to write this as an exponential expression. So we no longer want this written as a radical. So here's actually kind of like a little mini speed lesson. If you have something written in radical form, whatever your index is, that's actually going to be the numerator, or sorry, denominator. Whoop, wrong words. It's going to be the denominator of your fraction. And whatever the exponent is, that's going to be the numerator. Now for this one, it doesn't really matter if the exponent's inside the radical or off to the side. It behaves the same way. So for this one, it would be x to the power of 2 over 7. So the index tells you the type of radical. Number 18. We'll start off by putting it in radical form. So the denominator tells me the index. So the 5th root of 32 to the 2nd power. Well, the 5th root of 32 is just 2. Right? The 5th root of 32 is 2, because 2 to the 5th power is 32. So now this is saying 2 squared. Well, we know 2 squared. That's not too terrible. Number 19 is the exact same thing as number 17. Number 20 is the exact same thing as 18. Find the 3rd root of 27, raise it to the 4th power. 3rd root of 27 is 3. 3 to the 4th power, 3 times 3 times 3 times 3 is 81. All right, home stretch here. Whenever we are solving an equation with radicals, we want to make sure that the radical expression itself is isolated. And once it's isolated, you can already kind of see on problem 23, we're going to square both sides. So if I square a radical, all that happens is the radical just goes away and I'm left with whatever the radicand was. And if I square the other side, in this case I just get 25. That's not a difficult equation to solve now. What does get more challenging is when we have more complex variables, not complex variables, complex equations with variables on both sides. So in this case, I'm going to square to get rid of the radical, but I have to square the entire left side. So when I square that entire left side, I get a big trinomial. So u squared minus 8u plus 16, because that was u minus 4 kind of foiled onto itself. Once we have a u squared thrown into the mix, that's when we really like to see a 0 on the other side. So right here, we want to set it all equal to 0 because of the u squared. Then we'll factor, solve. You're going to get 2 answers. Whichever answer, when plugged back in, does not work for the original equation is called extraneous. So in this case, -4, if I plug that back in, would not work, because -4 minus 4, that's -8. I'm not going to get a negative number as a square root. Number 23, the exact same thing. Start off, square both sides. We've got a u squared, so I want to see it equal to 0. Stack everything over to one side. Factor it out, solve for u, you'll get 2 answers, plug both of those back in, Most of the time, it's going to be the negative number that's extraneous, but not always. So plug them both back in to check, and you're done. All right, that's it, folks. If you have any questions, please let me know. Good luck, have fun, be safe, roll tide.